In this video, we're going to look at two more examples on how we are going to apply conservation of energy to find the unknown. Now, let's take a look at the first question here. A ball is rolled going down an inclined plane from position A to B, and you're supposed to find the unknown speed of the ball at point B. And from the previous example, because the ball is released from rest, that's why when you equate applying conservation of energy, total energy at point A equals to total energy at point B. Of course, we're going to assume there's no air resistance or friction here. But why do I want to highlight this question is because some students, they are so used to always assuming that the position A, the first initial position, must be only GPE. That means the ball is released from rest. So you really have to look at the question carefully and ask yourself, what kind of energy does the ball possesses at this position? So if you look at it, the ball is already in motion. It has a speed of 2 meters per second. That means to say you must not forget the KE component plus the GPE of the ball at point A because it has a height of 5 meters. So, and then at point B, because there's a lowest ground, there's the reference height 0, so there's no GPE, so all the energy will be converted to KE of the ball at point B. So mgh here plus half mv square is equals to half mv square of the ball at point B. So once again, if the mass is not given, you can actually cancel off. But for this question, since the mass is given 2 kg, let's sub in the value times g, which is 10, and the height is 5 meters plus half times mass 2 times the speed of the ball, which is 2 meters per second. Do not forget the square, times half times 2 times the final speed of the ball at point B. And if you solve it, that will be 10.2 meters per second. So highlight again. So always do not assume that the ball at the first position here, the initial position, will be just GP and is released from rest. So really pay attention to the question. I can also extend this question to ask you what is the height of the ball when it's released, let's say at this position X. So what is the height and is released from rest? So that means to say, if at this point, because it's at rest, there's no KE, so all the energy will be GPE. So in other words, I can find the total energy at point X is equals to total energy at point A. Because using point A, I'm able to find the total energy of the system of the ball, because I know the KE and I know the GPE. So you can equate this together, and at point X, it is purely GPE. And at point A is a combination of GPE plus KE. So GPE mgh 2 times 10 and times the unknown height that the ball is released. So let it be h, and the GPE at point A 2 times 10 times the height 5 plus the KE half mv square, which is 2 square. And if you solve it, the unknown height that the ball is released at point X will be 5.2 meters. So that's how you solve it. There are some questions where the track actually goes in the loop in this way and then continue on, and the ball is over here. Some students assume that the ball at this point will be momentary at rest, but actually it's not. Remember, because the ball is released from the position X and this is the reference ground, as long as the ball is within this height, so at this point it will have a combination of PE plus KE. Okay, so the way to solve it is the same, even though the track is like a loop. Another type of question that will be asked is, if let's say the track continues on this way, and they ask you to mark on the path at where the ball will reach its maximum height. And because in this scenario where there's no air resistance and friction, so the ball will theoretically comes to here. Okay, because conservation of energy, all the energy it has here at point X will be converted to all the GPE at this point, so it will reach the same height in the ideal world. But in the real real world where there's friction and air resistance, the ball will actually reach somewhere around here below this point. Okay, and unless you give it a push, you give the system some more additional energy, then it is possible that the ball can go higher. So this part you have to understand. In the next question here, you are required to find the minimum speed of the ball at A in order to reach C. Okay, that's what's given in the question, and a lot of students will actually just consider these 2 points A and C and equate them together using conservation of energy, but that's wrong. You have to understand that in order for the ball to reach C, it must clear B, and that's the crucial point. And so in order to clear B, you must have a minimum speed. So I should be looking at the total energy at point A is equals to total energy at point B. So in order just to barely go over B, I can assume that the minimum speed that's required for the ball to just go over. So that means the KE at this point will be considered 0. And all the energy it has will be just GPE. So at point A, okay, because this is the lowest point, I'll treat this as the reference ground. So there's no GPE because there's no height. So all the energy will be KE at point A. And at point B, because like I said, just barely go over, I can assume that the K is 0. So all the energy will be GPE at point B. So half mv squared here is equals to mgh. So if you're not given the mass, I told you before, the mass is the like terms, I can cancel them away. So you're left with half v squared equals to 10 times the height 5. So v squared is equals to 100. So v will be 10 meter per second. So that will be the minimum speed in order to reach C. And of course, if you want to find the speed at point C, you can actually still do the same thing that you have learned. Equate point A, total energy equals to total energy at point C, where this is just KE, but at point C, it has a combination of GPE plus KE, and you know the GPE because you are given the height, and so you can find the speed at point C. So as long as you understand conservation of energy, you should be able to find all the unknowns.